All right, welcome everyone. Thanks for coming. I'm James Ward. This session is going to be about building reactive apps. So let's get started. So why we've been talking about reactive, why you've probably heard some buzz about reactive, is that really we're in the midst of some change in how we build software. And the drivers for that change I want to talk about real quickly are that users want their data to be in sync and real time. They want real-time collaboration built into their apps. Everyone wants the Google Docs style experience in every business application. They want instant feedback. They don't want to have to make round trips to the server to get validation errors. They want to see things just updated in real time. And they don't want to wait. And so these are some things that, of course, users have always wanted, but now we actually have some tools to be able to deliver it. And in order to do this, it requires kind of a new way to think about how we build our software. So that's really where reactive comes in, is that reactive is about building applications that are able to deliver these types of things to users. And so there's 4 tenets of reactive, and I'm not going to go into a lot of detail on them. You can check them out on reactivemanifesto.org, but just to highlight them real quickly, the first trait is responsive. So these are applications that react to users. And then built on top, what enables that is apps that react to load, and that's scalable. And then apps that react to failure, that's resilient. And then of course all this builds on top of a foundation that's event-driven, applications that react to events. So these things all work together in order to deliver these new types of experiences that our users want out of that. So if you want to learn more about the tenets of reactive and learn about how you can really think about these different things in new ways, check out the Reactive Manifesto. It really goes into a lot of detail. The nice thing about the manifesto is that it's technology agnostic. So really you could take these ideas and implement them in a lot of different places. So at TypeSafe, we have an implementation that I'll be showing you today for going reactive. It involves Play Framework and Akka. And then today, I'm going to be using Java 8 instead of Scala. The Scala would look pretty similar, but I'm going to go with Java 8 today. So there's kind of 3 different ways that we can go reactive that I'm going to talk about. First will be the reactive web. And we'll talk about reactive actors, and then we'll talk about reactive streams. So that's where we're going. So first, reactive web. The important things to think about in the reactive web are probably terms that you've heard before, which is async and non-blocking. And async and non-blocking is the way that we can deliver those ideas of reactive in a web application. So there's 4 different ways that we implement reactive in a web application. There's reactive requests, reactive composition, reactive push, and two-way reactive. So we'll dive into some details on what these actually look like. But in a nutshell, what async and non-blocking is that we don't want to block threads when they're not actually being used. Threads are actually a pretty important resource on the system. We don't want to just have tons and tons of them. We want to keep it down to really as small a number as possible, down to the number of cores on the CPU would be ideal. And so to do that, we need to not be blocking threads when we're just waiting for something on the other side of the network to come back. And that's just one example of where we can be non-blocking. It's kind of silly that we say async and non-blocking, because you actually can't be non-blocking without being async. You have to be async to be non-blocking. So we could just say non-blocking, but for some reason we say async and non-blocking, maybe just to highlight the fact that you have to be async to be non-blocking. So that's part of what we're going to be going through as we look at some code for how to build these types of reactive applications, is how do we be async first? We can be async and be blocking, but then how do we add non-blocking on top of that? So that's where we're going to go. To get started, I'm going to be writing some code, and I'm going to use something called Activator. It's a tool that TypeSafe created to create reactive applications. So let's go create a new application. So I've downloaded Activator and added it to my path. So now I can just say Activator new, and I'll give this a name. We'll call it Hello DevOps. And it's going to update my list of templates, which hopefully the network is working. Yep, looks good. Okay, and I'm going to use the hello play Java template to get started with. So there we go. I've got a new application now that I'm going to be using to build, to show these ideas of reactive to you. So first thing I'm going to do is I'm going to just run this application. So you can just do activator ~run. This is a play application with Akka, and we're going to be using Java, as I said. So it'll take a second to compile this application and get it up and running. I'm also going to be using IntelliJ to work on it. So let's just go open up this project here in IntelliJ. So that's the project here. And we'll open that up. So there we go. The application is now up and running on localhost 9000. So let's go check it out. Make sure everything looks good. So there we go. There we see our very basic application that we're going to be starting to work on. So there's a number of template applications in Activator, all sorts of different ones. This is kind of a scaffolding basic one to get you started, but there's a number of other applications or templates in Activator that will showcase all sorts of different parts of reactive. Some will focus on actors more, some will focus on futures, some are in Scala, some are in Java, some are in Java 8. So really many different templates to go choose from. You can check out the template catalog on typesafe.com, or you can also run Activator in a UI mode instead of in a command line mode, and you can explore the template catalog that way as well. Okay, so it looks like my IDE is ready, but I do need to, I think, make one change to it here. I do need to tell it that I am using Java 8, so let's go make that change here, and then we're going to have to reload this again. Not sure why it doesn't notice that, but that's okay. Okay. So here we go. We're going to start building a reactive application. So let me start first with the routes file so you can just see a little bit about how play routes requests. So in play, when I want to define a routing of how I'm going to handle a request, I do that in this routes file. So let's just go create a new route here to /foo, and that's going to call controllers.application.foo. Okay, so that's my controller, that's my route. Now let's go into my controller. This is my application.java. And now let's go create a new controller method. So this is going to be a static result is what it's going to return. You don't have to do static methods. That's the default because it's pretty simple. You can also do dependency injection, so you just don't have to be static, but I'm just going to stick with the static one for today. And so now what I'm going to do, this is not reactive yet, I'm just going to create a response here in this controller. So when the request comes in, it's going to come into this method, and then it's going to assemble a response, which is OK, status code 200, and then the response body is ASDF. So let's go try that out. Just go to /foo, and there we see that ASDF. So it's automatically recompiling this for me. So that's our typical regular controller method in play. So underneath the covers in play, this is actually implemented in an async and non-blocking way, but we didn't have to write the async code in this case because we're not actually doing anything async. So if we did want to make this controller async, instead of returning a result, what we're going to return is a promise of result. So a promise is going to give play a handle. Let's import that. That's going to give play a handle to something that will in the future produce a result. And so this is now how we go asynchronous, is we return not the thing, but we return a handle to something that will in the future return the thing. But that's the way that we go async. So now what I need to return is not the result, but I need to return a promise of the result. So let's create one of those. So I'm going to do f.promise and then just create a new promise. The first parameter here, I think there is only one parameter on this one. Oh, maybe there's two. Yeah, we need to, that should work. And it needs to be a function. So here's where we get into lambdas. There we go. So what I need to do is I can't just return the thing here. I have to create a function that will get executed to fulfill this thing. So that's how we are now asynchronous, is because now I have a function, that's a lambda function, that will produce the result when in this case, it's going to be produced immediately. So we're returning a promise of a result, but it's being fulfilled basically immediately by this function. So let's go check it out. Let's change the text here so we can verify that it works. When we hit reload, it should recompile. And then if I did everything correctly, now we see the new result there. So this time we were now async. We weren't non-blocking yet because we don't have anything to not block on. Really, this is pretty much what Play is doing underneath the covers with all of your controllers, but you don't have to have the extra boilerplate code if there's no reason to be async. If your code has nothing to not block on, then no reason to be async, and so you don't have to have this boilerplate code. So now let's actually take this to the next level where we become non-blocking and start being reactive. So there's an easy thing to not block on, which is just a timeout, like call me back in 5 seconds. So we're going to create, instead of just creating a promise that fulfills immediately, let's create a promise.delayed, and promise.delayed is now going to call this function in some amount of time. So there's a couple other parameters here. So the next one is how long I want to wait for. Let's wait for, let's just do 5, and then time unit dot seconds. So now we're returning again the promise of result, but we're not going to fulfill that result for 5 seconds. So let's try it out and make sure it actually works, and we can pull up the inspect window here to verify that it takes 5 seconds. So take a second to compile, and then it will make the request, and then you see that after 5 seconds that the response came back. So in that 5 seconds, my browser wheel was just spinning, but there was actually no threads allocated on the server for handling this request. There was a thread for when the request first came in, but then that method returned the promise of a result, and then after that 5 seconds, I called that function, that Lambda function, which produced the result and then sent the response back. But in that 5 second gap, there's actually no threads allocated to handling this request. So that means that I could get a bunch of these requests all at once, and they're all going to be just in this kind of waiting state, but there's not any threads allocated. So that's async and non-blocking in its simplest form. So pretty easy to get started building these reactive applications that are async and non-blocking. So that's kind of a trivial example, though, because why would we do this in our code? I don't know, probably not very useful to put arbitrary waiting like this into an application. So let's move on to something that's a bit more useful. An easy place to be async and non-blocking is making web requests. So some of the web request libraries out there are not async, but it's a pretty easy thing to make async, because there's usually when we make a web request, there's a request, and then there's some delay, and then there's a response, and we can be non-blocking in that delay time. So let's make a web request. So first, let's create our promise. And this is going to be a promise of a response. I'll import that here. And we'll call this thing RP. And then I'm going to use Play's web service client library and give it a URL. Let's just do jamesward.com. And then I'm going to call get. And get here, what that does is this makes a get request, or it schedules a get request to jamesward.com, but this returns now a promise of a response. So now I have a promise of a response from jamesward.com, but what this controller needs to output is a promise of a result. And the response is the read side of a result, of an HTTP response. The result is the write side of an HTTP response. So a little bit confusing in there, but we have the read side and the write side, and what I need to return is something that I've written the new result into, the new response into. And so what we need to do with this promise of response is transform it into a promise of a result. So we're going to return rp.map. And map is a very functional concept if you're not familiar with it. Real quickly, the map, what it's going to do is it's going to transform the thing inside of the thing. So we have the thing is the promise, and then the thing inside the promise is the response. And we want to transform not the promise, but the response that's inside of it. And so the map in this case, what actually happens is we're going to give it a function function that when the promise has been fulfilled, it will then call the function to do the transform on the response. But what we're going to get out of this is still going to be a promise. So we're still getting out a promise. So we're doing this all asynchronously. So let me show you the function that we're going to use here. So I do need to, let's give it an identifier here. So that's going to be our response. And then what we want to return is a result. So I'm going to create my result, okay. And then the result body is going to be our response. And then we'll just take the body out of that response and put that into the body of the result. And so now this function is transforming that promise of response into a promise of result. And it's doing it all async and non-blocking. So that function doesn't run until we have actually finished, till we've got the response back from jamesward.com. And then it's going to assemble the result and then return the result back to the browser. So let's go try it out here. Let's go hit reload in the browser. Take a second to compile. And then if the network is working, then there we see jamesward.com. I didn't set the content type, and we're just using text. Most of the time we'd be using JSON or some other serialized data, but for a simple example, we'll just use the text from my blog and see it there in the browser. So now let's go over again what actually happened. So in the browser, I hit refresh, and when I hit refresh, what happens is my browser makes a request to my Play server. That is going to make the connection, or create the promise that's going to make the connection to jamesward.com to get jamesward.com. And then at some point in time, I have two requests. The request from my browser to the server, and then the request from my server to jamesward.com. And there's some point in time where both of those requests are just going to be waiting on jamesward.com to respond. So in that amount of time, we can actually take those threads and give them to somebody else. We take them away, give them to somebody else, and then when the response comes back from jamesward.com, then we run it through that map function and transform it into the result, which then gets sent back down to my browser. So now we are doing reactive composition. We're composing together multiple reactive requests to create a fully non-blocking, async and non-blocking request through our system. Okay, so that's our very simple example. You may wonder, like, if all I'm doing is just making a request to my server and then making another request, why not just like do that on the same thread and just not worry about all the async stuff here. Where this really gets more interesting is when we want to do things in parallel. So that's where we're going to go next. Is we're going to make another request, and this one will be to twitter.com. And we'll call this one Twitter P. And so now we're basically scheduling two requests to be made, one to jamesward.com and one to twitter.com. And it's going to be up to the execution context, or the thread pool, to determine when and how we can run these requests. If we have enough threads in the thread pool, these things will go in parallel. If we don't, then they're going to have to wait until there's an open thread available. So there's no magic in terms of making this always absolutely be parallel, unless you throw just endless threads at the thing. But if we have enough threads, which hopefully we do because we are reactive, then we should be able to make both these requests in parallel. So now what I want to do is I want to return the result where I'm aggregating together the responses from jamesward.com and from twitter.com. So to do that, we need to get a little bit more functional here. And so the first thing we're going to do is I'm going to do not a map on the James Ward one. I'm actually going to do what's called a flat map. And I'll explain the reason for the flat map in a second. But so now in our callback function for when we're mapping jamesward.com, what I want to do is now take the Twitter P, and I'm going to map on that one. So we're going to run a map function on that, and we'll assign that to T. And now, in this deeply nested body of stuff, now is when I will have the responses back from jamesward.com and from twitter.com. So now is when we can actually do our OK. And what we're going to do is we're going to take let's take the Twitter body and append that to the jamesward.com body. And let's get all of our things in line here. So that one is right, then that one, and I think that's good. Okay. So what the flat map is doing, why we have to use flat map here, is that when I run this Twitter promise map, so when I run the map on the Twitter promise, the output of this is my promise of result. Right? So that's very similar to what we had before, So what I'm getting out of this is a promise of a result. And so now what this function is actually returning is a promise of result. And the reason why we do the flat map here is to take both of those promises and flatten them down into one promise. And that's why it's called a flat map, is because we're doing a map and a flatten. So we're doing the map function and then we're flattening it down. So let's go try it out and make sure that it works here. So there we go. Now we see twitter.com, and if we come a ways down, we see jamesward.com. So now we've taken these two text pages and aggregated them together. Obviously in a real world scenario, this is going to be with JSON data or with something other than text, but that's my simple example. Okay, so now we have reactive composition where we're actually doing things in parallel, and you can imagine that this becomes a pretty powerful way to be able to parallelize stuff and then just be able to take everything and in a fully async and non-blocking way be able to return that aggregated data. So that's our reactive composition. Let's go take a look back and see. We got through, let's go to the Java 8 code. So we got through that, and then I did want to take a minute to talk about reactive push. So reactive push is a way to do reactive, but just in one direction. We've been focusing on the ability to do a request and a response, so that's a reactive request. But of course we can also apply this to push. And so in the case of push, we're able to have a connection that's open. So to do push, we have to have an open connection, but we're only actually using a thread for that connection when we're actively pushing data down through that connection. So in the browser, there's a lot of different ways to do push. You can do comet style push that uses a never-ending iframe. You can use server sent events, which is the code that you're seeing here. You can also use WebSockets. The thing that's interesting about WebSockets is that instead of being a single direction like comet and server sent events, on a WebSocket channel you can push in both directions. So that's two-way reactive, where we have two push channels and are able to push data in both directions. So let's actually take a look at the WebSocket example. I think I can actually try to build this one. My code works. I didn't test this one, but let's go put in this and then I'll explain it here in a second. Import a few things. Looks good. Okay. I am going to need a new route to set up the WebSocket, so we'll do WS, and then we're going to call that WS, I think is what it was called. Nope, Echo is what it was called. There. Okay, so that's our route to be able to set up this WebSocket. And what I want to do is have now a JavaScript client for this WebSocket. So I'm going to do a very simple one here. Let's just go into let's create a new CoffeeScript file. So this will be in assets, JavaScripts, and then index.coffee. And I'm going to copy and paste this code too. So there's my CoffeeScript. So what this code is doing is making a WebSocket connection to localhost 9000/echo. We don't have to hard code those URLs. We could use plays reverse routing if we want to. And then when this WebSocket connection is open, I'm going to send a message up to the WebSocket. In this case, I'm sending strings, but of course I could send JSON data as well. And then when I get a message on the WebSocket, I'm just going to log that out to the console. So sending, if we take a look at the sending from the client to the server, we take a look at the Java code for how we implemented this WebSocket. It's a WebSocket of string. That's the data type that we're sending back and forth. As I said, we could do JSON or other data formats as well. So we're creating our new WebSocket, and then when the WebSocket is ready, we have an in and an out channel. And so the in channel we're going to be able to read messages off of. The out channel we're going to be able to write messages into. And so in is messages sent from the client to the server. Out is messages that I'm sending from the server down to the client. So I'm using a nice little Java 8 syntax here, a method handle, so that when we get a message, I'm going to call the out.write function to be able to just turn around and send the message that I got, send that back down to the browser. So that's my implementation. There's my index.coffee. One last thing we need to do is go into our actual UI here, our web UI, and I'm going to put in a script tag and set a source to, this is going to be assets, and then JavaScripts, and then index.min.js. And I think that should be good. Let's go try it out here. So there we go. We got our, failed handshake response 404 echo. Oh, I didn't call it echo in the route, so let's go fix that. Echo, there we go. So once this compiles, there we go, we see foo, very exciting, but what that came from was when the page loaded, we made the WebSocket connection, we sent a message up to the server, and the server just turned around and sent us a message back. So still kind of request response, but now these are two channels that I can push data at any time back and forth, and that connection that's now nailed open, we can go see it here in the inspect tab, this connection is now async and non-blocking. So this is not blocking any threads until I'm actively sending a message over that channel. So you can see there was a message up and then the message back down across that channel. So now we can be able to provide our users with these real-time interfaces, pushing data down to them, and not have to worry about the thread per connection limit that we usually have. So that is two-way reactive with WebSockets. So simple examples here, but I wanted to just give you an idea for how we can start to implement reactive in the case of the web with Play. Of course, you could also do this with Scala. You can also do it with Java without Java 8, up to you which way you want to go. So this is all based on Java NIO. Java NIO is the way that the JVM provides us to be able to do async and non-blocking I/O. So that's really the foundation of how we can be reactive on the JVM is with Java NIO. Play uses a networking library called Netty. That's the implementation of HTTP on top of Java NIO that's underneath the covers for all this stuff. Okay, so that's our async and non-blocking and two-way reactive. So now let's talk about reactive actors. So actors are a bit different of a model for doing reactive. What you saw before was all based on promises and futures. And so that's one way you can do it. It's nice and simple, as you saw. There's another way that we can do reactive, and that's with actors. And actors is an idea that's been around for a long time. Akka is an implementation of actors on the JVM. And really what these actors are is they're these event-driven workers. So they're outside of the request-response lifecycle, or can be outside of the request-response lifecycle. And an actor, it's really just nothing except for some memory on the heap until you send an actor a message. And the only way that you can interact with an actor is to send it a message. That's really the only way to talk to an actor or get it to do anything is you send it a message, and what actually happens is that message goes into a queue, and it's called the mailbox in Akka. And then when we can get a thread, we will take that message out of the queue and we'll give it to the actor. So we actually give the actor a thread, and now it can process that message. And once it's done processing that message, then it goes back to sleep, and it's only using memory on the heap, no threads. So usual actor system could have thousands of actors, millions of actors. They're so lightweight that we can really use them just for anything. And their life cycle can be really different. An actor life cycle could be milliseconds, or it could be the entire duration that an application is running. One of the benefits of the actor model is that really you're working in a way that the concurrency is being managed for you. So Akka is going to guarantee that only one thread at a time is being processed on a given actor instance. So it can only process one message at a time. So this now creates a really nice place to put mutable state. So if you have mutable state in your application, then put it inside of an actor, and you're going to be guaranteed that only one thread is going to be mutating that state at a time. This is really a much better programming model than the synchronized blocks that most of us are probably familiar with. So instead of using synchronized blocks, we put some mutable state into an actor, and now we're guaranteed that only one thread is going to be mutating that. Assuming that you don't let that mutable state leak out of your actor and let someone else mess with it. But if you don't do that, then you're guaranteed one thread at a time, thread safety for the state inside of that actor. So another important part of actors is that they're built into a hierarchy. So we have at the top of the actor hierarchy, the root of the actor hierarchy, we have the actor system. And then we build basically nodes of actors underneath that. And the reason why we do this, it comes from the Erlang days, is that now we have a way to do supervision. And supervision allows us to be able to handle failure. And this is how we really get to the resiliency part of reactive, is that if an actor fails for some reason, then the actor system, or the actor supervisor, it's the one above it in the hierarchy, can actually see that failure and determine what to do with that failure. The default supervisor just restarts the actor and tosses away the message that likely made it fail. But you can always override that supervision strategy and do all sorts of other different types of supervision. So it's up to you how you want to supervise your actors. But this allows you to put your breakable parts of your application down at the bottom of the actor hierarchy, and so that any failures there don't propagate up and then take down the whole system. And then another important part of the actor model is that these actors are location transparent. And so you can, of course, scale up inside of a JVM in order to add more actors in a system, and you can give it more threads and do things that way. But you can also scale out across a cluster. So when you send a message to an actor, that message could be in the same JVM, or it could be going across a network to the actor somewhere else on the cluster. So that's your brief little intro to actors and Akka. It's important to point out that, of course, this is all built on an event-driven model. So, of course, the tenet of reactive being event-driven is implemented in Akka. The only way that we can interact with the actor is to send it a message. So that immediately creates this event-driven way to interact with it, because now we have this decoupling between the sender and how the message actually then gets delivered to the actor. So let's take a simple little example here so you can see what this looks like. So let's create a new Java class. We'll put it in actors, and we'll call this foo actor. And in the Java API, we need to extend from the untyped actor class. One important point of actors is that the messages that you can send and the messages that actors can send, they're not typed. So what we're going to actually be able to receive is any type of message. And so there's no way to constrain that the message that gets sent. So that's why it's called untyped actor, is that when we implement the onReceive method, you'll see that it is taking a message of type object here. So now in onReceive, we could check the type of that message and have different behavior based on the message that we've received. In this case, it's only going to be receiving one type of message, so I'm not going to do anything special here. What we're going to do is, let's just copy a couple lines here and then I'll explain them. So I'm going to have, first, like we've seen before, I'm going to have something async and non-blocking. I'm going to have this request to jamesward.com. So that's async and non-blocking inside of the actor. And so that's going to make this request out to jamesward.com, just like we've seen before. But because this response is coming back on a different thread, we have to use a pattern in Akka called pipe. And what pipe does is it really is able to preserve the context context of where we were before we went into this async callback world. Because that response is going to come back on possibly a different thread. And so it's possible that when I actually try to do something with this response, that response is different. The sender is what could change in this case. That sender could actually be a reference to a different instance of the actor. So we've lost our context. We're in this async world, and so patterns.pipe allows us to wrap that stuff up, and so that we don't lose these references across that async world. So here what we're doing is in pipe, the parameters here are the future, the thing that I'm actually going to be waiting for. You'll see I had to do .wrapped there. The reason is that this pipe method takes a future of a response, and what my web service client library has produced is a promise of a response. So .wrapped just gets me to that future of response. And then the second parameter here is the execution context, or the thread pool that we want to give this thing to execute on when it comes back. And then we're going to say .to, that is now who we're going to send a message to with this result once it's finished. And so in this case, I'm using the sender. So whoever sent me this message, that's going to be the person that I respond back to with this response. Of course, the sender could be anyone. I can send messages to anyone in the actor system. So that's our simple little event-driven actor there. So now let's go build just a client of this actor. Because we've been working in web apps, an easy example is to make a web controller the client to this actor. So I'll copy a little bit more code, and then we'll walk through what it's doing. And we'll have to import a few things here. Okay. And foo actor, and Akka, and patterns. It's a lot of imports. Okay. So what we're doing is we're going to the Akka system in play, and we're saying create a new actor, and then we use this props.create is the way to tell it how to create the actor. So we're doing props.create to create this foo actor, and you'll see what I get back isn't actually a foo actor. What I get back is an actor ref. And this is an important part of Akka, is that I don't work directly with the instances. I work with references to the actor. The reason for that is that because of that supervision model, the actual actor instance could change, or it could be, it could have died across somewhere else on the network. So I don't want to work with an actual instance of this thing. I want to work with a reference to the actor. And now what I can do is I can send messages to the actor reference, and that's how I then can queue a message to go into the actor and be processed by the actor. So I've created my foo actor. Now what I want to do is I want to send that actor a message. And if we just want to send it a message, just fire and forget the message, then there's an API where you just say tell. I can say, I'll show you, it's foo actor and then .tell. So then we send it. The parameters here are the message that we want to send, and then the reference to the person who's sending it. In this case, I'm not actually in code that's inside of an actor, so I would probably assign this the sender to be, there's an actor called dead letters that is where just any messages go that aren't handled, that are not sent to a valid actor. So that would probably be the actor that I would use for this actor ref. But so that's how we just send a message. But in this case, back to the request response model. Don't know why. I guess I'm a web guy, so I keep getting stuck in the model of request response. But what I'm going to do is I'm going to send this actor a message, but then I want to get a response back from it. And of course, that's a very valid way to use actors. You don't have to use them that way. They can be fully one way. So what I'm doing is I'm doing an ask. And an ask is a send, and then it's a handle to what this actor is going to send me back. So that handle, of course, is in a future. So if we look at the response there, we're going to get back a future of object. So it's typed object because these are untyped actors, so it's sending an object back. I don't know what that type is going to be. So I send the foo actor a message. The message that I'm sending is just a string, doesn't matter because I'm not actually using that message on the actor side. And then I have to provide a amount of time that I'm willing to wait for this response to come back. So in this case I've said, wait up to 5 seconds for this response to come back. If I don't get a response in 5 seconds, then my promise will fail with a failed state. So a promise can be in 3 states. It can be either pending, so I don't have a result yet. A promise can be in I have a value, a completed state, and then it can also be in a failed state or an error state. So those are the 3 states that a promise can be in. And so if this fails with a timeout, then the promise will complete with an error, and that error will be a timeout exception. So I get back out of this a promise of object, and then what I want to do is take that promise of object, and really what I want to send back is a promise of result. And so the actual message that I'm getting back, I'm just going to cast to the response. I know that's what it's going to be, but of course I could check that ahead of time. And so I'm going to cast that, and then I'm going to get the response body out, and then I'm going to put that into the result, and I'm using the map on the promise to transform from a promise of object into a promise of result. So let's try it out, and then I'll tell you why this is wrong or what's missing. Now let's go back to foo. So we should see jamesward.com. So there we go, it worked. The request came in. This request, this function that's handling this request, this exits immediately. Well, it runs a few lines of code, but then exits. There's no waiting going on here, right? It's still fully async and non-blocking. So what it does is it's creating an instance of the actor, it's sending a message to that actor, and then getting back a handle to something that will in the future have the response from that actor. And then that message goes into the mailbox gets a thread, goes into James Ward, into the foo actor on receive method. That then makes a request, an async and non-blocking request to jamesward.com, which is itself a promise. When that promise fulfills, then I'm going to send that message back to the sender, which fulfills this function here, or this promise, and runs this function here. So that's now async and non-blocking all the way through from the web request to the actor and to the web service client. There's one problem with this here is that now I've got this foo actor and I haven't done anything with it. So now it's just sitting out there taking up memory on the heap. So really I should clean up my actor after I'm done with it. So this could be a very, in this case, the life cycle of my actor would be the request and the full request and response. I could take this actor and I could share it across everyone, right? So if I wanted everyone in the system to all go through this actor, basically gate everything down in my application to a single thread, I could do that. I could also use routing actors. Routing actors can actually talk to a pool of actors underneath them. So you can say, create me a routing actor that's based on the round robin routing mechanism and give it 20 actor instances. And now I'm just going to send a message to the routing actor and it's going to round robin through the actors underneath it. So all sorts of different ways that we could structure the life cycle of these things. And of course, then we can also build them in hierarchies and have messages being sent to children and messages being sent to parents and all sorts of things. So we're just kind of touching the surface of the actor model. But there's some really great templates in Activator to explore the actor model in a whole lot more detail. So I definitely encourage you to check that out. Okay, so that is a reactive web request with actors. So I wanted to talk about the next piece of the next way to do reactive, which is called Reactive Streams, and this is super exciting. We just announced this today. So this is a cross-company collaboration between, there's a bunch of different people that worked on this, and we can go to the website here to take a look at the list. So TypeSafe, Oracle, Pivotal, Netflix, Spray, Twitter, Red Hat, Doug Lee helped as well, and Eric Meyer. So we got all these people together and said, hey, let's create a standard way to do reactive I/O with back pressure on the JVM. And so what we've created through this group of people is we have a specification of what reactive streams should look like. We have an API defined for the Java interfaces. We have an SPI, and then a test harness, so a test compatibility kit. So we've created all those things and just announced this today. So definitely encourage you, if you're interested in reactive I/O and how that what that looks like with back pressure built in, check out reactive-streams.org and find out more about that. So it's pretty exciting. It's a super simple API. You know, the super simple things really take a lot of smart people to get them that simple, and they really did a good job of creating a really easily understandable API for doing reactive I/O with back pressure. For those of you that aren't familiar with what back pressure is, I'll give you a simple example. So if you have a file upload coming from your user to your web server, and then you're taking that file upload and let's say sending it to Amazon S3, then you really don't want the user to send more data than you can push to S3. That may or may not always be the case, but you really don't want to build up these giant buffers on your server if your client is pushing bytes faster than you can push them to the next place. And so back pressure allows you to actually tell the client, hey, back off for a while, and so it slows down its send until you can catch up. And this allows you to avoid building up buffers. So yeah, and it's all async and non-blocking. So we do that in an async and non-blocking way. There is a synchronous way to be able to do back pressure. You basically just like read things really slowly, but that's blocking. And so one of the unique things about reactive streams is now we can do that back pressure in a non-blocking way. So pretty cool. Definitely encourage you to check that out. Okay, so there's a lot of templates, as I mentioned, in Activator to get you started. Some of the ones that'll be good to start with are reactive stocks. It's a great sample application that shows you reactive composition, shows you reactive push with WebSockets, and there's also now a Java 8 edition of that. So the default one is built with Java and just Java pre-Java 8 and Scala, but we now have one that's all Java 8. Reactive maps is a really great one to explore the actor model more and how you can really have a resilient cluster of actors, and that uses play for WebSockets and that sort of thing. There's an Akka Streams activator template now that you can check out, so if you want to check out the Reactive Streams that I was talking about, check out the Akka Streams. Akka Streams is the implementation of Reactive Streams on top of Akka. So there's a template to learn more about that. And then there's, if you want to see more of the Java 8 stuff, check out a couple templates, Reactive Java 8 and Play Framework, and Hello Akka Java 8. So lots of great templates to get you started, but we have a couple minutes left if there are any questions. Any questions? All right. All right, well, I'll be around afterwards if you have any other questions, but I hope you enjoyed it. Thanks for coming. Thanks.